In this video, we will discuss estimating a population mean. It's very rare that we will know a population standard deviation sigma, but not the population mean mu. As a result, we first focus on the case where we know neither the mean nor the standard deviation. As discussed in a previous lesson, the sample mean x bar is an unbiased estimator of the population mean mu. Also, for many populations, sample means tend to vary less than other measures of center. For these reasons, the sample mean is the best point estimate of the population mean. Because even the best point estimate gives us no indication of how accurate it is, we use a confidence interval, which consists of a range of values instead of just a single value. The next slide gives the key elements for constructing a confidence interval estimate of a population mean mu in the common situation where sigma is not known. Constructing a confidence interval used to estimate a population mean has the following requirements. The sample is a simple random sample, and either or both of these conditions are satisfied. The population is normally distributed, or n is greater than 30. The format for the confidence interval is x bar minus e is less than mu is less than x bar plus e, where x bar is the sample mean, e is the margin of error, and mu is the population mean. The margin of error, e equals t sub alpha over 2 times s over the square root of n. We use n minus 1 degrees of freedom, where n is the sample size. The critical value, t sub alpha over 2, is the critical t value separating an area of alpha over 2 in the right tail of the student t distribution. And the degrees of freedom are n minus 1 is the number of degrees of freedom used when finding the critical value. The round-off rule. For original data, when using an original set of data values, round the confidence interval limits to one more decimal place than is used for the original set of data. The summary statistics. When using the summary statistics of n, x bar and s, round the confidence interval limits to the same number of decimal places used for the sample mean. Normality. The method for finding a confidence interval estimate of mu is robust against a departure from normality, which means that the normality requirement is loose. This distribution need not be perfectly bell-shaped, but it should appear to be somewhat symmetric with one mode and no outliers. Sample size n greater than 30. This is a common guideline, but sample sizes of 15 to 30 are adequate if the population appears to have a distribution that is not far from being normal and there are no outliers. For some population distributions that are extremely far from normal, the sample size might need to be larger than 30. In this section, we use a student t distribution, which is commonly referred to as a t distribution. I include this history because you are college students and it involves beer. The t distribution was developed by a Guinness Brewery employee named William Gossett, who needed a distribution that could be used with small samples. The brewery prohibited publication of research results, but Gossett got around this by publishing under the pseudonym Student. Over the next few slides, we will look at some key points about the student t distribution, which, in the interest of not typing the word student over and over, I will refer to as a t distribution. T distribution. If a population has a normal distribution, then the distribution of t equals x bar minus mu over s over the square root of n is a t distribution for all samples of size n. Degrees of freedom. Finding a critical value t sub alpha over 2 requires a value for the degrees of freedom, or df. In general, the number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all data values. For the methods of this section, the number of degrees is the sample size minus 1. So the degrees of freedom are equal to n minus 1. Finding the critical value t sub alpha over 2. A critical value t sub alpha over 2 can be found using technology or table A3 on page 686. Technology can be used with any number of degrees of freedom, but table A3 can be used for select numbers of degrees of freedom only. Using table A3 to find a critical value of t sub alpha over 2, which I will do throughout these slides, but the table does not include the exact number of degrees of freedom You could use the closest value, or you could be conservative by using the next lower number of degrees of freedom found in the table. The t-distribution is different for different sample sizes. The t-distribution has the same general symmetric bell shape as the standard normal deviation, but has more variability with wider distributions, as we expect with small samples. The t-distribution has a mean of t equals 0, just as the standard normal distribution has a mean of z equals 0. The standard deviation of the t-distribution varies with the sample size, but is greater than 1, unlike the standard normal distribution, which has sigma equals 1. As the sample size n gets larger, the t-distribution gets closer to the standard normal distribution. Confidence intervals can easily be constructed with technology, or they can be manually constructed by using the following procedure. First, verify that the two requirements are satisfied. The sample is a simple random sample and the population is normally distributed, or n is greater than 30. With sigma unknown, use n-1 degrees of freedom and use technology or a t-distribution table, such as table A3, to find the critical value t sub alpha over 2 that corresponds to the desired confidence level. Evaluate the margin of error using E equals t sub alpha over 2 times s divided by the square root of n. Using the value of the calculated margin of error E and the value of the sample mean x bar, substitute those values into our expression for the confidence interval x bar minus E is less than mu is less than x bar plus E. Round the resulting confidence interval limits as described in the key elements on page 317 in the textbook. Find the critical value t sub alpha over 2 corresponding to a 95% confidence level given that the sample has size n equals 15. Because n equals 15, the degrees of freedom is n-1 equals 14. The 95% confidence interval confidence level corresponds to alpha equals 0.05, so there is an area of 0.025 in each of the two tails of the t-distribution, as shown in the figure below. To find the critical value using table A3, use the column with 0.05 for the area in two tails, or the column with 0.025 for the area in one tail. The number of degrees of freedom is df equals n-1 equals 14. We get t sub alpha over 2 equals t sub 0.025 equals 2.145. Listed below are weights, hectograms, or Hg, of randomly selected girls at birth, based on data from the National Center for Health Statistics. Here are the summary statistics: n equals 15, x bar equals 30.9 Hg, and s equals 2.9 hectograms. Use the sample data to construct a 95% confidence interval for the mean birth weights of girls. Here are the data scores. We don't really need them right now. We must first verify that the requirements are satisfied. 1, the sample is a simple random sample. And 2, because the sample size is n equals 15, the requirement that the population is normally distributed or the sample size is greater than 30 can be satisfied only if the data appear to be from a normally distributed population. As with most data sets of natural phenomena, the birth weights of girls are normally distributed. The requirements are satisfied. Using table A3, the critical value of t sub 0.025 equals 2.145, as shown in the previous example. We now find the margin of error E. E equals t sub alpha over 2 times s over the square root of n, which is 2.145 times 2.9 over the square root of 15, which is equal to 1.606126. With x bar equals 30.9 hectograms and E equals 1.606126 hectograms, we construct the confidence interval as follows, rounding to 1 decimal place. X bar minus E is less than mu, which is less than x bar plus E. 30.9 minus 1.606126 is less than mu, is less than 30.9 plus 1.606126. 29.3 hectograms is less than mu, is less than 32.5 hectograms. We are 95% confident that the limits of 29.3 hectograms and 32.5 hectograms actually do contain the value of the population mean mu. If we were to collect many different random samples of 15 newborn girls and find the mean weight in each sample, about 95% of the resulting confidence intervals should contain the value of the mean weight of all newborn girls. We will pause here and continue in the next video.